For most of human history, time was measured in days, seasons, and years, not billions of years. The idea that the entire universe could have an age is astonishingly recent. So, how did we figure out that the universe is 13.8 billion years old? The answer comes from centuries of science, from ancient rocks beneath our feet to faint whispers from the dawn of time. Our story starts not in space, but here on Earth. In the late 1700s, a Scottish geologist named James Hutton looked at valleys carved by rivers and sediments turned into stone. He realized that Earth's processes took an unimaginably long time, far longer than anyone had believed. He famously wrote, "No vestige of a beginning, no prospect of an end." By the 1800s, geologists like Charles Lyell expanded on Hutton's ideas. They showed that the slow, steady processes shaping Earth, erosion, mountain building, fossil formation, hinted at an ancient planet millions of years old. But the true age of the Earth remained a mystery until the dawn of the atomic age. At the turn of the 20th century, scientists discovered radioactivity, and with it, a brand new way to tell time. They found that certain elements, like uranium, decay into other elements at fixed, predictable rates. By studying these atomic clocks buried inside rocks, scientists could measure just how long they'd been ticking. Using this method, geophysicist Claire Patterson calculated that Earth and the entire solar system formed 4.54 billion years ago. For the first time, we had a reliable clock for the planet itself. But there was another puzzle. If the Earth was billions of years old, how could the sun have kept shining for that long? In the 1860s, Lord Kelvin believed the sun's energy came from simple heat or gravitational collapse. If that were true, it could only shine for about 30 million years, far too short to fit with Earth's geological record. The answer came decades later, in 1938, when Hans Bethe realized that the sun's energy came from nuclear fusion, the process of turning hydrogen into helium in its core. That discovery not only explained the sun's brilliance, but linked the lifetimes of stars to the ages of planets, all governed by the same physics. Meanwhile, another mystery was unfolding in the night sky. In 1929, Edwin Hubble, using the 100-inch Hooker telescope on Mount Wilson, measured the light from distant galaxies. He discovered that their light was stretched, redshifted, showing that galaxies were moving away from each other. The universe was expanding. If everything is expanding now, then long ago, everything must have been closer together, leading to the idea of a cosmic beginning. But early estimates of how fast the universe was expanding gave strange results. Some suggested the universe was younger than the Earth itself. Astronomers realized their distance measurements were off and spent decades refining them, slowly piecing together a more accurate cosmic timeline. By the mid-1900s, astronomers turned to globular clusters, dense balls of ancient stars orbiting our galaxy. They estimated the stars' ages by watching when they began to leave the main sequence, the stage when stars run out of hydrogen fuel and expand into red giants. Early results suggested ages between 10 and 15 billion years. With space telescopes like Hubble, those estimates became more precise, about 12 to 13 billion years. This set a lower limit for how old the universe must be. Then, in 1964, two engineers, Arno Penzias and Robert Wilson, stumbled upon a faint hiss in their radio antenna. No matter how much they cleaned or adjusted it, the noise wouldn't go away. That noise turned out to be the cosmic microwave background, the cooled afterglow of the Big Bang itself. It was light left over from when the universe was just 380,000 years old. Later satellites, COBE, WMAP, and Planck, mapped this glow in incredible detail. From its faint ripples, scientists calculated the most precise number yet. The universe is 13.80 plus or minus 0.02 billion years old. Today, scientists use 3 independent cosmic clocks to confirm that number. First, stellar evolution, the life cycles of stars. Second, Type 1a supernovae, exploding stars that serve as standard candles for measuring distances. And third, the cosmic microwave background, a snapshot of the universe's infancy. All 3 tell the same story, and they match beautifully. It's also important to remember, the universe isn't expanding into something. Space itself is stretching. Like raisins in rising dough, galaxies move apart because the dough, or space-time, expands between them. The farther away a galaxy is, the older the light we see. So when we look far into space, we're literally looking back in time. That number, so casually mentioned today, is the product of generations of curiosity and wonder. And in this vast, ancient cosmos, one small species on one small planet has done something extraordinary. We've measured not just our own history, but the age of time itself.